Hello everyone, I hope you are doing well. This is the first video of Applied BIOSTATISTICS channel, and I am Max Shah. Of course, this is my nickname, and I wanted to start the first video of the channel with the Applied Statistics and Experimental Design. Of course, this is a course and includes a series of videos. The first video is about the normal and the distribution, and we mainly focus in applied statistics and experimental design, and it means we practically focus on the important and main tools in statistics. As you know, there are different distributions and tools that we don't necessarily use them, and we use the important ones to analyze our data, like t-student, chi-squre, f-test, and some experimental designs like CRD, RCBD, Latin square, and factorial designs. So in this course I try to mainly focus on them and easily explain them to you so that you can choose the best test, a statistical test, to analyze your data. And also I try to use the effective tools like SPSS, SAS, and R, so that you can conveniently use them to analyze your data. So let's get started, guys. So the normal distribution is the most important distribution is in statistics, and most of the statistical reasoning, like the decision to see if something is significant or not, is based of normal distribution. And as you know, the distribution of most natural phenomenon is normal, like weight, IQ, height, I don't know, the yield of crops. And if you measure several samples and draw a plot like histogram, you see that the distribution is somehow like a normal distribution or a bell-shaped distribution, and we talk about it further. And even if distribution is not normal, we can transfer it to become normal, and we have to transfer the not normal distributions and make them to be normal, and we discuss it later, and I will teach you how to test normality, and if your distribution is not normal, how to actually normalize your data. So what are the characteristics of normal distribution? The first one, and one of the most important ones, is a bell-shaped curve. And as you see, as you see here, the shape of normal distribution is like a bell. And of course this one, as you know, and I will explain to you what are these or what are these. And the other important characteristics is the normal distribution is symmetrical around the mean. It means if you, for example, see this is the mean of our distribution, and the left side and right side are symmetrical. The other characteristic of the normal distribution is about the mean and standard deviation of a normal distribution. We describe a normal distribution by two actually parameters. The first one mean, and the second one it's a standard deviation. For example, if you look at these distributions, they all share a mean. It means it's 10 right here, but they have different standard deviation. For example, the green one, its standard deviation is 1, this one is 2, and this one is 3, and of course it covers longer and varied distribution here. And if we look at these ones, as you see, they are all have same standard deviation but different means. For example, this one, the blue one, its means is 900, and this one and the purple one, all of them has different means but same distribution. Sorry, different standard deviation. And the last one I want to discuss is the mean, median, and mode. In normal distribution, here the middle one, this one, it is a normal distribution and there is no skewness in this distribution. The mean, median, and mode are all of them are here, and in normal distribution it is all of them are the same. But for example, in this one it is negatively skewed. The mean, median, and mode are not the same, and they are in different positions. And this one also, it is positively skewed, and the mode, median, and mean are located in different distributions. So this one, which is a normal distribution, there is no skew, and the mean, median, and mode are exactly in the same position. So until now we discussed about normal distribution, but what is a standard normal distribution? We call it Z or Z distribution. If you see this formula, if in a distribution we have several samples, several measurements. If we subtract each measurement from the mean and divided it to the standard deviation, we get the z-score of each measurement, and we will see something like that. Here it is a standard distribution, a standard normal distribution that 90 something about approximately 99.7% of data is between -3 and 3, and 95% of data is between -2 and 2, and 68% of data is between -1 and 1. In normal distribution, we have, for example, if the mean is 10, let me show you here, it's more obvious in here. As you know, for example, this is a normal distribution, and in normal distribution we have our mean plus our standard deviation, our mean plus our 2 times standard deviation, and 3 times, and minus 3 times standard deviation, 2 times, and our mean minus our standard deviation. In normal distribution, we have something like that. This is exactly these intervals are exactly the same here, but the only difference is we don't have an exact mean for our distribution. It can be anything. For example, 100, I don't know, uh, 10, 200, anything. And if we calculate the standard deviation of our distribution and we calculate these items, you can see that, for example, approximately 100% and exactly 99.72% of our measurements are between our mean minus 3 times of our standard deviation. This is about the normal distribution. But if you actually convert your measurement to z-scores, you can see that this happens. It means that all of the distribution, all of the z distribution, standard normal distribution, actually always have 0 as their means and 1 as their standard deviation. This is about all distributions. So let me clarify it for you by an example. Imagine I have gone to a farm, to a wheat farm, and I have measured the height of some wheats in that farm, and I calculated the mean of my measurements. It is 100 centimeters, and I have calculated the variance and the standard deviation, and it is 10. If I actually draw a plot of my measurements, you will see that something like that happens. My mean is 100, and something around roughly 100% of my measurements are between 70 centimeters to 130 centimeters, as we discussed. And if I want to make a standard normal distribution, I need to change and convert my measurements to z-scores. For example, if I want to convert the 100 to z-score, I have to first subtract 100 from the mean. Mean is 100, and divide it to 10, and I will have 0. And if I do the same thing with 110, 120, 130, and 90, 80, and 70, I will have these results, which all of them are my z-scores. And if I make my plot, this will be like that, exactly like that. My mean for my z-scores, my new actually scores, the mean will be 0, and my standard deviation will be 1. And as we discussed, roughly 100% of my data will be between -3 and 3. So this is the z-score table, and we use it to get the probability of a desired value. For example, here we have -1.2, and we want to see the probability of values equal or fewer or equal or less than minus 1.2. Here in the z table, here we have different values from 0 to minus 3.4, and for example, uh, as we discussed, for minus 1, this is the probability for the values equal or less than minus 3, and for minus 1.2, this is the probability for values equal or less than minus 1.2, and they are the probability level. For example, this is the 5% level of probability, and this is for 99% of probability, but usually we use this one because this is the exact value. And as you see, for example, we you know that the probability of values equal or less than 0 is 50%, because as you know, we discussed the distribution, the normal and z distributions are symmetrical, and the probability for values equal and less than 0 is 50%. So as you can hear, this is. So let me elucidate it more with an example. Imagine we have measured the weight of 10,000 people and calculated the z values for each measurement. As you saw in the last example, you can measure something, for example, the weight or IQ or anything else, and you can convert each measurement to z values. And in this example, we have measured the weight of 10,000 of people and calculated the z values. The probability for z values equal or less than 1 minus 1.2 is actually 0.1151. It means that for our measurements, 1,151 people have z values equal or less than minus 1.2, and actually this was minus 1.2. I wrote it wrongly, but there is no difference. You'll see that there is no difference between the probability of 1.2 and minus 1.2. So this is how we can calculate the probability of something. For example, we have measured the weight of 10,000 people, and we can convert all of them to z values and see, for example, how many people have the specific z value. So let's look at this distribution. As you can see, this is minus 1.2 and this is plus 1.2, and I want to repeat this important fact that the probability of this area means the probability of values equal or less than minus 1.2. This area, the probability of this area is exactly the same with this area, means the values equal or more than 1 minus 2. So if we as you can see, the probability of z equal or less than minus 1.2 is this value, and exactly the probability of value z scores actually more or equal to 1.2 is exactly the same with this one. So as you see, the z distribution and normal distribution, both of them are symmetrical, and we can use this fantastic characteristic of the normal distribution to calculate the probability of any value here. And I want to stress something again. As you saw in the table, in this table, we have the actually minus values from actually minus, this is not minus 0, we don't have minus 0, this is 0, and minus 0.1. So for example, as you see here, if we want to calculate the probability for values more or equal than 1.2, we use the probability of values equal or less than 1.2, because as you saw here, this table is designed to have the minus values. So of course I will have several examples so you can learn it deeply. So here we have this value minus 0.45, and we want to calculate the probability for the values equal or more than this value minus 0.45. Before that, I want to tell you that the area under the curve for normal and z distributions are 1. It means that if I measure the probability of this part and add it to the probability of this part, the result will be 1. It means that 100% of probability. So let's calculate this part. You can find it in the z-score table, and the probability for the z values equal or less than minus 0.45 is actually 0.3263. And as the area under the curve is 1, we can simply calculate the probability for this area by subtracting this value from 1, and we can get the probability of this area, which is 0.6736. And for example, in this distribution, if we want to actually measure the probability of values between minus 1 and 1, the probability of this area is 0.1586, and exactly because, as we discussed, the z distribution and normal distribution are symmetrical, so the probability of this area is the same with this area, so we can easily calculate the probability of this area, and the probability of values between minus 1 and 1 is equal to 1 minus 2 times of the p-values equal or less than minus 1. because this value and this value are the same. And if we actually multiply this value by 2, we will have the probability of both sides, and if we subtract it from 1, we will have the probability of this area. And now you found out that why the probability of values between -1 and mine we had in previous slides was something around 68%, as you saw. I think you saw here the probability between -1 and 1 was 68. And in the next examples I will tell you why the probability between for example -3 and 3 is 99.7%. So let's see the next example here, and this is another important one. This number -1.64, like the previous examples. This area, the probability of this area is 0.05, and also this area. And if we want to calculate the probability of this area, like the previous slide, if we subtract the 2 times of this value from 1, we will have 90%. So the probability of the values equal the probability of values between -1.64 and 1.64 is 90%. And what about -2.58 and 2.58? We actually use the same approach, and we will have 99%. So the values between these two values is the probability is 99%. Okay, let's see this example, and imagine I have the marks of students' statistics exam, and the distribution is normal. It means is 100, means the mean of the students' marks. And I have also calculated the standard deviation, and it is 15. So let's calculate the following items. We want to calculate the probability of marks equal or less than 127. So for that, for calculate this probability, we need to actually calculate the z-score. So we need to calculate the z-score of 127. And as you remember, this is our equation, z plus 2, this equation. And if we want to calculate the z-score, we need to subtract 127 from 100 and divide it to 15, because 15 is our standard deviation and 100 is the mean of our distribution, and this is our x, which we want to convert it to a z-score. So if we calculate this equation, we will have the probability of z values equal or less than 1.8. And as you know, the probability of, as we discussed, this is actually z equal or less than 1.8 is equal to 1 minus the probability of z scores equal or less than minus 1.8. And finally we will have 96% as the R probability for the marks equal or less than 127. What about the probability of marks between 88 and 112? Like the previous part, we need to convert 88 and 112 to z values. If we do that, we have the minus 0.8 and the actually we have minus 0.8 and plus 0.8, which finally, as we discussed in previous slides, if we want to calculate the probability of this item, we need to subtract 2 times of the probability of z's equal or less than minus 0.8 from 1, and we will have something around 57%, means 57% of the marks are between 88 and 112. And what about the probability of marks more or equal than 140? Like the previous items, we calculate the z score of 140, which is 2 times 7, and as the z distribution is symmetrical, it is exactly equal to the probability of z scores equal or less than minus 2.7, and this is less than 1%, so it is something around 0.35% of the marks are more than 104. Okay, let's see another example. If the weights of 800 people has normal distribution with a mean equal to 66 kilograms and a standard deviation equal to 5 kilograms, we need to calculate the number of peoples who their weights are, for example, between 65 and 70 kilograms. This problem do not want us to actually calculate the probability, and we need to calculate the number of the people between these numbers. So we need first to calculate the probability, and easily we can find the number. So let's first convert the 65 and 70 to z scores. If we use 66 and 5 as our mean and standard deviation, we will have the probability of z scores between minus 0.2 and 0.8. And let me show you that we need to calculate the probability of this area between minus 0.2 to 0.8. So this is the probability, this area is the probability of z scores equal or less than 0.2, and this area is the probability of z scores equal or more than 0.8. So if we have the probability of this area and this area and subtract them from 1, we can get the probability of this area between minus 0.2 to 0.8. And the other thing, as you know, because our distribution is symmetrical, the probability of z scores equal or more than 0.8 is equal to the probability of the z scores equal or less than minus 0.8. So if we calculate this, we will have this one, and finally we will have 0.3674. This is the probability of the weight between the weight of people between 65 to 70. And for calculating the number, we just easily need to multiply our probability by the total number of our measurements, which we will have approximately 294 people who their weights are between 65 to 70. And if we want to actually calculate the number of people more than 72 kilograms, we can easily calculate the z-score. And as you remember, the z-score for values equal or more than 1.2 is 0.1151. And if we, so this is our probability, and if we multiply our probability by the total number of measured weights, we will have 92. So roughly 92 people have more than 72 kilograms, of course equal or more than 72 kilograms as their weights. Okay guys, in this part I want to show you how you can use R language, which is a language especially for statistics, and it is a powerful tool for you to use to analyze your data. You can use it for, I don't know, statistics, bioinformatics, draw your plots, visualization, and many other things. So you can either install the RStudio and R and use that, or I have another way which is easier. The result is the same, but I think the Google Colab is a very good environment for you to use R. So I'm gonna use Google Colab. You can search Google Colab in Google and open the Google research, the Colab research Google. After that, you will see this screen. So before that, of course, you need to sign into Google, and you can open a new notebook. For example, I click on new notebook, and a new notebook will be opened for me, and I can use it. So let me make some cells. Okay, right here you can change the name. For example, I write the statistics, and To use R, you need to click here and click on change runtime type. So here you can use Python or R. I choose R and click on save. So this is a R environment. This is our environment, and I can use it, and you can use it to run your R codes. And there is no difference, of course, between this one and using R Studio on your operation system. And you can save it. For example, I click on save and I can save it, and then I can use my notebook. If I click on open notebook, I can use my previous notebooks, and I have already saved the applied statistics and experimental design. I can open it, and I have some codes in this notebook, and we will review it together. So it is, as I told you, it is an effective way for using Python and R, and as we are using R, this is a very good idea to use Google Colab. So in R you can use R norm to make whatever number you want with a special mean and a special standard deviation. So I want to make a variable like not a variable, I want to specify a, and I want to put in 100 numbers in it between 10 and a standard deviation 2. And the R norm will give us normal distribution, means we will have 100 numbers with the normal distribution. So if I push Control and Enter together, it will execute my code. So it's ready. So we have A, and if we want to see A, we can just write it and push Control and A, and we will have 100 numbers which are normal, actually have normal distribution, and we can visualize it. We can visualize with hist, and we can will define A, and the bricks is number of these columns. I want 20 columns, so I set 20 for bricks, and as you can see, it is somehow a normal distribution, but not exactly, because if you increase the number of your samples, you'll get more and more actually bell-shaped distribution. So let this time create 1000 numbers, so, and get the histogram of it. As you see, this is 100 and this is 1000. More and more bell-shaped distribution. And if, for example, we create 10,000, let's see what will happen. So as you can see, it is very good bell-shaped distribution for us. And I don't know if it is, I think it is 10 millions. Yeah, 10 millions. I want to make 10 millions numbers as C, and visualize it this time with 100 bricks. So let's do that, and actually you can see it is a completely bell-shaped distribution with 10 millions numbers, and you can increase the brick so that you can get this shape. Yeah, and as you can see, our mean is 10, and approximately 99% of our data is between 10 as our means, plus and minus 3 times of our standard deviation, which will be between actually 16 and 4 right here. If we imagine 4 is here and 16 is here, then approximately 99% of our data will be between these two numbers. So if you use this code, you can get your plot in a PDF file. Oh, I don't want to execute it, but if you are watching this video and you need your file as a PDF, and after that convert it to other formats, you can use this code. And I want to define D with 1000 numbers, and it means its mean is 10 and standard deviation 2. And I want to convert all of these numbers to z scores and see what will happen. Let's first I define the standard normal and I put a 0 in it, and with this code I will actually command the R to use I actually for I in 1 to length of D, which means 1000. The length of D is 1000. So I define I from 1 to the length of D, which is 100, and I want R to all of the i's, which is, as I told you, 1 to 100, to do this equation, do this formula, get every one of these, for example the first one, the second one, until the 1000th one, because I define I as 1 to 1000. Get all of them, subtract all of them from 10, which is our means, and divide it to 2. And as you know, and as you guess, this is the formula for calculating z-scores. And if I do it, let's do it, my D standard normal, I show it with the stand norm. It will be a normal standard distribution, and if I visualize them, as you can see, this is the D itself has 10 and has 2 as a standard deviation, so something between 16 and 4. The most of the data actually is between these two, which means minus 3 times of our standard deviation and plus 3 times of our standard deviation. So we expected, when we converted our measurements, our values to z values, we expect the 10 to be converted to 0 and all of them to be between minus 3 and 3. And as you can see, this is what happens. And we converted our values, all of them, to the z-scores. And if this code needs to be explained more, please tell me in comments and I will explain it in the next video more, so that you can get what happened here. And the other good things about R is P norm. You can get any value for Z, any Z value, and you can get the actually probability. For example, for 2 we have this probability. For example, for 1.2 we have 88. And before that, let me first get the minus point. And as you saw in the slides, it is 0.1150, and this is somewhere here. But if I get the probability of 1.2, I will get this value. Why? Because it gives you the probability of the left side. So when you get the minus 1.2, you get the probability of this area. This is minus 1.2, and when you get the 1.2, you get this area from here to all of there to here. So you can get that, and you can calculate any probability you want. It gives you easily. And yeah, that's it for this session. Thank you for watching. I hope it was helpful for you guys, and please comment your idea about this course, and if there is anything you want to recommend me, please tell me in the comments. And if you liked this video or videos like this, because I wanna make more videos like this, and a lot of different videos about statistics and maybe genetics and bioinformatics. Please like the channel for more videos. It will be a huge enthusiasm for me to make more videos. So thank you for watching. See you. Thank you.